we're going to continue our session on the active flux, and I'm pleased to introduce Dr. Santiago Hernández León, who is the director of the Institute of Oceanography and Global Change in the Canary Islands, and also professor of zoology in the Marine Sciences School at the University of Las Palmas, Gran Canaria. And I've known Santiago a very long time. He's been working on zooplankton ecology, physiology, and from the Arctic to the Antarctic, all over the world's oceans, and has been studying active flux for a good part of that time. He's been working over 3 decades as a biological oceanographer. So we're very lucky to have him here today to talk some more about the active flux. So thank you, Santiago.
Thank you very much. Thank you very much for the introduction and also for inviting me to give this talk. I'm going to review some active flux by Zooplankton and Micronekton. I will talk about the variability of this flux and some gaps and some note about the CDR. There is a lot of work about the vertical migration in the literature after the Second World War. And we have this work by Vinogradov that he put on the screen, the ladder of migration. But there were a lot of work by many researchers working on that and saying that these animals were transporting carbon downward. But until the paper by Alain Longers in 1990, he was the first to quantify the respiratory flux, the true transport of carbon to the deep water. So there is some pioneers' works, other by Sang and Dam in 1997, introducing the term of mortality. So not only the respiration, but also the mortality of death, and also a pioneering work by Steinberg et al. In 2000, introducing the excretion of the dissolved organic carbon by these migrants. So I'm going to talk about first about the sport sensolampid. So it's the carbon entering in the permanent thermocline, and also first about zooplankton. And this is the way we sample the zooplankton biomass. This is with the longest hardy plankton recorder. The resolution is very high, but we sample by day and by night, and we convert this zooplankton biomass into respiration rates, or measuring the electron transfer system activity, the enzymatic proxy for respiration, or converting to respiration using equations relating body size and temperature, as the equations by Ikeda in 1985 and later. So the day minus night respiration rates is in here in the deep waters is the true respiratory flux, or true mortality flux, or dissolved organic excretion, carbon excretion. So many workers only sample in the upper 200 meters. This is a normal and easy way to calculate by day and by night the migrant biomass. And they sometimes measure the ETS in the deep water, sometimes use all these equations by Ikeda. And this is the papers related to active flux by zooplankton. And the most striking signature is the high variability related to the particle organic carbon flux. So sometimes, like in here in the Pacific, in the tropical Pacific, is between 4 and 6% of the particle flux. Sometimes is 24, sometimes is 90, sometimes it's almost 200. So the variability is really very high. Why we have this impressive variability related to POC flux? So this is a sampling in the Canary Current. We are going to talk about these oceanic stations. There is some upwelling stations also using this Longus hardy plankton recorder with a very high resolution. So what we sample from in the spring and fall, looks that during the spring the biomass is less than during fall. During the oligotrophic season in fall, we have more biomass in the deep waters than during the spring, that is more productive area. And more striking is this is the electron transfer system activity, and we found an important difference between spring and fall in the mesopelagic layer. So in the mesopelagic, during spring, we have more respiration than during fall. And this is temperature, the anomaly of temperature between spring and fall. So there is no too much difference in temperature, so something like 1 degree sometimes. So this is not the causative phenomenon for this. But if we look at the body weight of the animals during the spring, is much. The body weight is lower than during fall. So there is a seasonality in this body weight of these animals, probably because they are growing during spring, the productive season there, and during fall they are larger animals. So in here, this is the question. This is the answer. Smaller animals have much more respiration rate, much higher respiration rates than large animals. So if we took all the data we have around the Canary Islands, we are starting to see the seasonality of this respiratory flux. So in April, May is higher than in fall. And this is more or less related. This is a 50 years average of biomass in the epipelagic zone in the Canary Current. So what we observe is that after the bloom in the upper layer, so we have an increase in the deeper water. So there is a transference of carbon from the upper layers to these deep waters due to this dual vertical migration. So this is also really important because it's the interannual variability of this active flux. This is data from the Bermuda time series station, so where we have biomass by day in the epipelagic, by night, and the migrant values. So they also estimate the active transport by these animals. So it's increasing. So there is also no seasonality, impressive seasonality change, but also in the interannual variability of this. We need this data much more all around the world. We need this time series in the mesopelagic. So I'm not going to talk about lipid pump, but because the previous presentation talked about this. But this is another important contribution by Jonah Steer et al., who introduced the lipid pump in the active flux estimations. So what about micronekton? Because you know, the paper by Longus was in 1990, and in 2001, Idaka et al., they measured the active flux by decapods, mesopelagic fish, large euphosis, and they studying this micronekton, they observed that the flux by micronekton was higher than the flux by zooplankton, and in only 2 stations, and with a lot of assumptions in here, because the mesopelagic fish escaped from the trolls. But he advised that we are measuring half of the story, so we have to go into this flux by micronekton. And 10 years later or more, Davison measured the respiratory flux in mesopelagic fish, and the message was that the zooplankton and mesopelagic fish provide similar amounts of carbon downward, so they are transporting similar. So this was really an important message, and after that we start to work, use observe this. This is the only data we have in zooplankton and micronekton, or only in micronekton. So we are starting in this research. We have really very few data. So this is in north of the Canary Islands, Ariza et al. They measure micronekton with an Oseki troll. It's 5 square meters. And they measure also zooplankton and micronekton abundance and biomass, and they measure the electron transfer system activity. So they provide the second estimation of zooplankton and micronekton. So the migrant biomass was rather similar in zooplankton and micronekton, but micronekton was only composed by mesopelagic fish. So, and the respiratory flux was higher by zooplankton because they are smaller animals, so they respire more. But also all the transport in the micronekton was made by fish in these waters. So in another cruise, we sampled from the very oligotrophic waters of Brazil to the equator, the upwelling in the equator, to the Guinea Dome in here, and to the oceanic upwelling of Northwest Africa. Not the coastal with large diatoms, etc., but in the oceanic upwelling in this cruise. So in here, the stratification was really important. And when we went to the north, here is the upwelling, so stratification is lower and lower. This is the oxy minimum sum, and this is the deep chlorophyll maximum, so very deep in the oligotrophic waters, and increasing shallower and shallower until the oceanic upwelling of Northwest Africa there. So we sampled with mock-nets for zooplankton and with the Mesopelagos troll for micronekton. This is a 40 square meter mouth, very large. So the most striking result was that in the oligotrophic area, most of the flux was driven by particles. 80%, almost 80% of the flux was driven by particles, and a few by micronekton and zooplankton. But in this grading of productivity, so the flux, the importance of the flux, the particle flux was decreasing and increasing the flux by zooplankton and micronekton. And in here, we estimate a 50% of capture efficiency. So it's very conservative. Probably this is much larger in here. But in the Guinea Dome, most of the flux was driven by the micronekton and zooplankton. And we leave this area and enter in the upwelling area, and again, the animals, the pelagic fauna has a very large importance. So the production, the productivity is very important in here. And when we observe, this is the POC flux in this area. At high productivity, we don't have too much sedimentation, probably because we are not in the upwelling, in the coastal upwelling with the large cells, but in the oceanic, that the cells are smaller, but also because there is a lot of zooplankton there, and probably they are fragmenting all the particles. A lot of zooplankton process all these particles as Dan Mayer advised. So the this is the total active flux by zooplankton and micronekton in relation to primary production. So the slope is much higher. So there is the animals are more sensitive. And in fact, in Stockel et al. In the Costa Rica dome, they observed in this very productive waters that almost all the flux was driven by the pelagic fauna also. So, so primary productivity is important for active flux. So I would like to also, this is a paper by Kwong et al. In 2020 in different eddies around Australia, and they also measure this micronekton carbon, but also is important others like pyrosomids or salps sometimes, you know, and we have to give some attention not only to mesopelagic fish or decapods, all this, but also all these organisms that are also really important. And this is an example in the coastal upwelling by Stockel et al. In 2023, where the active flux was 1/3 of the sinking flux. But in here, in the coastal upwelling, you have these very large cells, so the sinking is really important. And they also measure subduction. So I propose this for the future, you know, to measure the 3 pumps. I think it's very important. It's very difficult because you have to put quite different people on board, but I think this is important. And this is another example in the Southern Ocean, but Annabelle et al., where they observe this very, very low respiratory flux, but it's due to the low temperature there. Because when she corrected for temperature, so the amount was really similar. So in the cold waters, the respiratory flux, because respiration is lower. Okay, so what about sequestration in the sense of lab pit? So the carbon entering in the thermohaline circulation. So the carbon will remain there for centuries. So we observed this during this is the Malaspina cruise all around the world. And this is the LADCP backscatter. So we can do this acoustic work until 4,000 meters. So we observed high backscatter in the productive areas, in here in the equator, in here reaching South Africa and leaving South Africa, reaching Australia, in the equator, in the upwelling area in the Pacific equator, and reaching America. This is the oxygen minimum zone. This is a blue hole there, and also reaching Europe. So all the productivity in the upper layers, this is the deep scattering layer, of course. So there is a relationship between the zooplankton biomass in the epipelagic, mesopelagic, and basipelagic. So converging to in the very large net primary production. So in here, the biomass of zooplankton is almost the same in the upper, in the epipelagic, mesopelagic, and basipelagic. This is not new because Koppelman and Viker in 2007, they observed this is in the Mediterranean, the typical profile of zooplankton until 4,000 meters. But during the bloom in the Mediterranean, they observed this. So in biomass and abundance, the biomass was almost the same in all the water column. So this is important because there is also a transference of carbon to the deep water, to the basipelagic layers. So I'm going to talk about some gaps very, very fast. The first is that when we balance respiration and the carbon entering in the mesopelagic and bathypelagic, in the mesopelagic we are having now more data, and we are able to balance in some way the respiration in the mesopelagic layer. But in the bathypelagic layer, we have no idea. We are starting to have some data about zooplankton and micronekton respiration, and also in the productive zones, there is also a lack of data. So we have to, this is a twilight symposium, but we have to go deeper next time. So this is a cruise we made in 2018, and we observed there was also a gradient of productivity here, more productivity in the north. So this is the oxygen minimum zone, the salinity and temperature, and we observed these sharp migrations there. But in here, in the northern part, in the very productive area, there was 3 layers of fish there going up and down every day. It was impressive, but the problem, we cannot capture them. So they avoid the net because the net, when it's coming, is promoting bioluminescence, so the animals evade the, so they are very clever. So, but we have to go into this important migration in here. Also, this paper by Van Haren in 2019, he observed this is a moored ADCP at 2,000 meters, looking upward. So at 1,500 meters, he observed organisms migrating. We don't know who they are. And during fall, they stop in there, so they are probably consuming lipids in there, so it's a seasonal migration. And the next year start to move again in up and down, and during fall they remain here. So, and also there is a very large variability. This was in between Azores and the Canary Islands. So who are these animals? So in February we have a cruise and observe below 800 meters all this stuff there. A lot of decapods and mesopelagic fish in below the oxygen minimum zone, and almost nothing during the day in the upper layers, and during the night all around mainly the decapods are all around the water column, so going up and down. So these animals probably are sequestering carbon, and we cannot see them if we go to the acoustics. We see this, but it's permanent, and below 1,000 meters with noise only, nothing. But in the evening, they start to aggregate in here, and you can see a very sharp migration from the deep waters of these animals. So when they go back to these depths below 800 meters, so they respire in there, so they are sequestering carbon there. So this is important. So how can quantify the mesopelagic fish? That this is a real problem we have right now. And we have been using this video system attached to the rosette, and this acoustic zooplankton fish profilers with 4 frequencies. So now we can see individuals, they escape from the rosette because they also see the rosette coming in because it promotes bioluminescence. But now we can count them. So this is a very interesting approach, but of course the problem of acoustic is that we don't know who they are. So this is also interesting. The EK60 see this landscape and the acoustic zooplankton fish profiler in the profile. We can see different. So at the same frequency, we see a different profile. Probably because the EK60 they are counting a large volume, sampling a very very large volume. So this should be also studied. So this is our rosette with the So with all this illumination, so we are able to do these profiles. and we can sample the, for instance, decapods and gelatinous plankton, and sometimes some fish, large fish like this, but no mesopelagic fish at all, nothing. They evade, they escape from the rosette. So we can do some very nice gelatinous plankton profiles. And but what about the mesopelagic fish? So we know about this behavior of mesopelagic fish by Steinkarber and colleagues that he published recently. But this is the three-dimensional behavior, swimming behavior of mesopelagic fish. So they, starting here, they goes up very fast for 1 meter, and they adaptate the swim bladder to the new depth and so on. So they migrate not like we imagine, but they goes up 1 meter and they stay there for a long time. So they another 1 meter and so on. So they reach the upper layer. So this is a way we said, how can we fool these these animals? So we put a camera here, so a very stable camera without moving too much, in order to avoid as much as possible the bioluminescence promoted by the camera. This is our camera with the red lights and all this. This is a new version of the profiler, and so you can see in there. And with this camera, in this case at 176 meters, we were able to sample. Yeah, this is a 2 mesopelagic fish, 4.5 centimeters to calibrate. The images are not good because we have to. The cameras are really very expensive. So first, it's better to test if we see the animals, so you can see the mesopelagic fish passing in front of the camera. So with what is important is that with this a black animal over a black background, this is the worst scenario for a photographer. We can see now in white. So we are able to see sometimes two animals passing in front of the camera, but they don't migrate as a school, but one by one. So we can see some examples of these are really large. We have two cameras in order to size them in the near future, but now it's working. So we would like to this is the 2 mesopelagic fish, 4.5 centimeters, and this is another example of the animals passing in front of the. So now we can see the mesopelagic fish, and we can count as they pass in front of the camera in the way up for this migration. So sometimes they goes very fast because this is 1 meter, vertical migration. Sometimes they remain in here for long, and we can see something, looking here. What's that? I don't know. So okay. So when we count the animals, so this is the sunset, and this is minutes after sunset. So we can see at 176 meters the animals passing in front of the camera. So this is a way to count them in the way up. So this is the first time they do not evade, or at least we don't know. Probably there is other species that they see the red light and goes away. And this is one example, and this is at 154 meters in a very cloudy day, and they reach the upper, in this case, this depth before in the other case. So at the end of the nautical twilight, we do not observe or observe 1 or 2 or 3 animals only. So in this way, we made a rough estimation of biomass, mesopelagic biomass, fish biomass. So when we sample with the net, we sample with this, the rough estimation is 1 order of magnitude higher, the biomass. So when Coslow and many others uses a 14% capture efficiency, so they are right. They are right. And probably is more biomass. We have to finish this work. But I think it's interesting because people around the world can start to do this. I'm going to briefly talk about the effect of the DL vertical migrants upon epipelagic communities. So this is work by Prihar Tato with acoustics all around the world in the Malaspina cruise. So there is a window here during the full moon that the animals are in here and not in the upper layers. So during this full moon, the zooplankton, epipelagic zooplankton, non-migrator grows without predation. And this has been observed in the lakes, and we have observed this increase many times. So the migrants during full moon do not reach the upper layer, so the zooplankton in here grows without predation. So there is a lunar cycle. We have some papers, this is one of them, in which we observe this lunar cycle mainly during the late winter bloom in the subtropical waters. So, so what is important is that they modify during this small window, because it's just in the full moon and a few days after and a few days later, they change the community. So during most of the month, this is the normal pathway in the ocean. The microzooplankton is grazing the primary producers, a few zooplankton. So almost all the energy goes to the microbial pathway. So there is a lot of respiration, low gravitational flux. But during this window, small window, we have more zooplankton. So they feed on microzooplankton. So all these small cells typical of oligotrophic system, pico, nano, microzooplankton, is converted to large particles, to zooplankton. So when the full moon passes, so all these animals come, feed on the zooplankton, and transport all this zooplankton biomass to deep waters by active flux. So this is an idea for a future carbon dioxide removal, that if we illuminate very weak, you know, the light of the moon is it's nothing, you know, less than 0.3 lux with a buoy or a drone or sail drone or something like that. So the animals will remain in here, so the zooplankton will grow. If it grows, so if the window is 10 days, and not 3 days, but 10 days, or 14 or 12 days or 14 days, so the zooplankton will grow much more. So after this bloom, the migrants, when we switch off the light, you know, the migrants come, feed on the zooplankton, and transport all this zooplankton. So this is an idea I think is worth to explore in the future. So this proposal is based on the concept of biomanipulation, no geoengineering. It was used in lakes for restoring the lakes. So in lakes, for restoration, they take away the fish. So all they recover the lake and they put the fish again. So this is inspired in this. We don't need to dump particles or have an enormous number of devices for upwelling. It's based in the theory of ecology of bottom-up and top-down controls, and it's based in increasing the efficiency of the biological pump. There is no need to increase primary production, and I think, personally, that is environmentally friendly, but probably there is some indirect effect that need to be studied, as in every work related to CDR. So, in summary, zooplankton and micronekton transport similar amounts of carbon in subtropical waters, and active flux is similar to passive flux, but passive flux is 80% in oligotrophic waters, most of the waters in the planet, yeah? And it's the opposite, 80% is active flux in very productive waters. And the active flux increase much more than gravitational flux at higher primary production. The increase in primary production is transported downward to the basipelagic zones. So this is something we have to go into in the next years. Need for zooplankton and micronekton time series. This is a serious message. Okay, thank you. So we need to measure in different areas of the world of this. So DL vertical migrants impacts the epipelagic zooplankton community as observed during the lunar cycles. So this top-down effect could change the paradigm of CDR methods. Let's see. But we have a lot of work in front. So thank you very much.
Thank you, Santiago. Do we have questions?
Hello, thank you very much. Claire Webster here from the University of St Andrews. I was just looking at the graph, the really nice graph you put up of the Mesopelagos net when you went across the Atlantic Ocean. And I was just wondering what your opinion was, more of a conjecture on if, for example, the catch probability of that net is even close to what Roland Proud used in his catch probability estimations. If we're underestimating the biomass of fish, I think the abundance is a factor of 7, but the biomass is like a factor of 20 because we're missing big fish more, then what that graph might look like. And then again, also your opinion on, as you spoke about the iron fertilization and your really good idea at the end about the moon and how that might be better as soon as we don't know a lot about the biomass of fish and how that might all interact. Just your opinion on all of this.
Difficult question.
Thank you.
Yeah, with the Mesopelagos, the capture, compared with, for instance, with the Oseki, we capture larger animals. So the people engaged in this taxonomy are very happy with the large net, but the efficiency is really very low. We use it in our paper. We say with the 20% efficiency is this number, and with the 50% efficiency is this other number. So the uncertainty is really very high. So now we are starting this, and so we need other approaches like this video system. And you can see the fish seems large, like in your study, you know. So in the study by Claire Webster, using acoustic, they also, this split bin, it was split bin acoustic, so they can measure the animals. So the Mesopelagic fish were higher than the Mesopelagos captured. So I think this is the way to combine all these systems. The other was. We at the beginning proposed to use these lunar cycles in combination with the iron fertilization. So this was a proposal long ago, and after that it was forbidden, all these experiments and all this. But I think the efficiency would be much higher if you fertilize in the right time in relation to the lunar cycle. But I think there is no need to. In the future, we are not going to fertilize all the ocean, the Southern Ocean. This is probably a crazy idea. So we will fertilize patches or eddies or something like that. So all around the world, after we are sure that this works, not promote any problem. But with this, it's almost the same. So we will eliminate patches of the ocean. But we have a decade, 10 years. We need 10 years for that. But there is no hurry because, until the emissions, the emission must go down, and during that time, all these methods will work. Because, the amount of the increase in CO2 is lower, so you can capture this the CO2 that will remain after zero emissions in the atmosphere. So I think
I like your optimism.
Oh, great. Thank you so much, Santiago. That was really fascinating. And I'm really curious about learning more about the CDR that you're proposing. And I'm interested in what you think the largest indirect effects may be and how you would assess them.
You say the indirect effects. Yes. In here, for instance, the tuna fish feed on this animal, this mesopelagic fish, and also the dolphins and all this. So I think the dolphins and the tuna fish can go deeper during the full moon, and we observed that the swordfish was going to 500 meters and feeding in there, and other tuna were going down. So they are able to move in the water column. So probably there is no effect for them. But for instance, the pups of some animals are not able to dive much. So probably we have to study this. And of course, to do these experiments far from the coast where the pups of some animals are producing, the animals are reproducing there. I made a list of possible indirect effects. I don't remember all of them, but this was important. And also the seabirds, and because the seabirds also, they feed with the moonlight, and also the fish larvae, that they feed during the day only, but sometimes they feed during the night because there is moonlight, and they can see the shadows of the copepods. So probably for them will be positive. But yeah, there are, when you are playing with nature, you have to be very careful, very, very careful about what are you doing. So it's not good to do it and go away. So
very impressive talk. I also had another question about the CDR. So to have this have any effect, you would have to run the intervention for some period of time, right? Like you would need some amount of time where you're illuminating the water column. How long would be too long for then negatively impacting the productivity of the deeper micronekton?
no, the question is how long?
So like you would have to run this the artificial illumination for some period of time, yeah. And then that will have impacts on the organisms that are not migrating up and not being able to feed. But how long would be too long before you then kind of
in nature the window is probably a week or something like that, But if you start to widen this for 12 days or 14 days, in the models you see the increase in zooplankton. So we have to play with that, increasing only 2 days more, 3 days more, and so on. So and to study all the effect of the DL vertical migrant. But you know, when the DL vertical migrants goes up, this is an indirect effect is that they do not feed in the zooplankton biomass, but they are feeding also in there. In fact, they migrate. They migrate from 500 meters to 100 meters. So they do not reach the upper layers. So they continue feeding. But we have to study this, how, you know, if they are affected or not.
Thanks for a great talk. It's Dan Mayer, University of Aberdeen. Just following on from the previous question, is there anything at all known about how long a mesopelagic fish can survive without feeding? What's their starvation response, and how long can you switch these lights or leave them switched on for and not starve these animals to death?
In fact, the mesopelagic fish do not migrate every day. So they, you know, it's very dangerous to go to the upper layer. So there is a paper by Woodstock et al. He was in here last week, and he calculated this. They calculate this time. So mesopelagic fish normally spend 1, 2, or 3 days without migrating. This is part of the variability in the mesopelagic biomass, because it's too risky to go up into the upper layers, because the predators are there, the tuna fish and all the cetaceans, all this. So they can stay for this time, but they also continues feeding. They migrate if to 100 meters depth. So they continue feeding, but not so much as they go to the upper layers. So, but you're right, she's right. We have to study this before, so by far.
Got a microphone, so maybe it's me. Hi, it's Carol Robinson from the University of East Anglia in the UK. Thank you, Santiago, for a really nice talk. I was quite disappointed to hear that bats is the only place where we have these time series of data. I wondered, as a community, if we were writing a proposal to encourage or start or enhance a particular time series study, where should it be? Which is the priority ecosystem that we should be looking at next, if not bats?
I'll just note there's one at HOT too, the Hawaii Ocean Time
yeah,
Series.
I had assumed so. Yeah. And also, is there not one in the Southern Ocean, or you know, where should we be focusing this work next?
This time series stations in Hawaii and Bermuda, and there is another one in the, and there are many that is not they do not sample every month, but as in the Canaries, we have a time series working during spring and fall, you know, 2 times per year. But we are constructing a very long time series. So I think it's something we have to take seriously, because almost all the uncertainties we have is because we do not sample in different years, because there is an important internormal variability as observed in the bats data, but also we have to put the not only zooplankton but micronekton, and this is the problem, because in normal oceanographic cruises, you know, people working with nets consume a lot of time. So if you go with a zooplankton net, a small zooplankton net, oh, big, yeah, we are having problems with the time. So imagine a troll. We spent 2 days in a station, 2 days in a station, because we go with the Mognes during day and during night, and with the Mesopelagos by day and by night, and the rosettes by day and by night, and others, WBAT and many others. So it's a lot of work, and you cannot join with physical oceanography, for instance, because you know, they use the rosette and no more. So yeah, it's a different sampling strategy, of course. But this is a real difficulty. But we need it. We need this time series.
Well, I'd like to thank Santiago again, and thanks very much.